Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So our final speaker is Tony Hay, and I feel disadvantaged because he had a copy of my biography when he introduced me, and I don't have a copy of his. But he will say he's written a totally cool book he's got a draft of there. And the only problem with, if you look at it right now, you'll be so distracted you won't listen to his talk. But otherwise, Tony Hay.
Great, thanks very much. Okay, so I was trying to think of something to entertain you, so I thought I would title my title something that you might not have heard of, which is The Third Age of Computing, which is an idea from Butler Lamson. See if I can get this to work. Okay, so Third Age of Computing. So I'll come to that. So the outline for the talk is, I should explain that I come from CMU Northwest, all right? Because we have Peter Lee, we had Rick Rashid, of course. We now have Peter Lee and Jeanette. And just this week I learned that Harry Shum, who actually is an alum from here, is now coming back to be Peter Lee's boss in the research and technology division. So we have good connections with CMU, as you all know. So what I wanted to say, first of all, was a little bit about computational thinking, if you like, applied to science, which was what Jim Gray was doing. It was actually using advanced computer science techniques to help scientists who were drowning in data, and that was where it came from. And so I'll talk about Jim's idea of the fourth paradigm, and I used to do e-science, and I'll explain what I think that is. But then I'll end with some words about the future, which I think the cloud will be in your future, machine learning certainly will be in your future, and I'll end with a sort of explanation of what Butler's grand sweep of computing. So, I mean, you've seen all these things. Data of all types. Yes, we have lots of data for commercial transactions and all these things, and Twitter feeds and mining those is extremely important, search data and so on for commercial companies, but also it's also true in the sciences. Now you have satellites and you have high throughput gene sequencing. The problem is now not that we can take ages sequencing one human, but we'll all have our genes sequenced very rapidly, and the problem will then become of getting interesting facts and interesting useful stuff from all that data, and that's the challenge in almost every field of science, environmental science, in biological science, and anywhere you look, particle physics, astronomy, and so on. So if you look in Bing, a good search engine, which I'm sure you're all familiar with, as far as I know, my family are one of the few users of Bing in Europe, but in the US, it is used a fair amount. And if I look up data scientist, you find that computer scientists have good employment, because data scientist, the hottest job you haven't heard of, the role of the future, what is a data scientist? So there's a whole literature. This was some weeks ago. So distilling about what is a data scientist, in our e-science workshop we had in Chicago a year ago, we had 2 sessions on data science. One was given by computer scientists, and it was exactly what you'd expect, about machine learning, data analysis, and so on. And the other one was given by librarians, information scientists, and it was all about data stewardship, how you look after the data, how you capture the provenance, and how you do the metadata and all that sort of stuff. And in fact, it involves all 3 of these, and rarely would a data scientist have all these skills. So data science is a rather large area, and it covers things from information science, or the iSchool movement, to data analysis, machine learning, and so on, to actually going getting the data, reducing it down to something useful. So that was, I think, what Jim was trying to get at. Jim started working with scientists, I think, in the 1990s, he started working with astronomy because they had data sets which were larger than the biggest relational data sets you had in commercial practice at the time. That's not true now, but it was then, and he wanted to extend SQL Server, play with the web services and things like that. And he chose astronomy because they were drowning in data, and their data was of absolutely no commercial value. So you could actually do things with it, you could analyze it and play with it. So Jim came up with the idea of the fourth paradigm. So I'm sure most of you heard about this now. Thousands of years ago, we've been doing experimental science, as you know, making measurements of the stars and things since the Egyptians and so on. And since the days of Galileo, Maxwell, we've condensed much of that into laws of nature, and then you can explore those theoretically. I used to be a theoretical physicist, so you can actually explore that, analyze it in various situations, make predictions for experiment, which you can go and do. And those have been the traditional two ways of doing experimental and theoretical paradigms for doing science, and they're the way that have served us very well for hundreds of years. But in the 1950s, of course, we invented digital computers, and that enables you to do different things. And Ken Wilson, who won the Nobel Prize for particle physics in the 70s, called computational science the third paradigm, because it enabled you to explore situations that you couldn't do experiments. You can't do experiments on climate change. Well, we are doing one, but it's only one. Perhaps we'd like to understand what the drivers of climate change and so on. Can you do galaxy formation and black hole collisions and things like that? So computational science looks at different things. And to do that, you need to teach graduate students different skills. They need to know about algorithms. They need to know about numerical methods. They need to know about, in particular, high-performance parallel systems and how to program in parallel on those systems, as you heard from Guy. So a different set of skills. It doesn't replace theory and experiment, but it's a new way of exploring science. What Jim was seeing in the last decade was the emergence of a third set of, a new set of skills, a fourth set of skills, if you like, for data-intensive science. So you have these throughput instruments, you have simulations and supercomputers which generate petabytes of data, you have sensor networks which generate huge amounts of data coming in. Data from all sides are overwhelming scientists, and what they need to do is to know how to manage this data. And so when I was doing a complementary side to this, eScience was, if you like, the set of tools that enable you to manage this data for analysis and data mining, for data visualization, and for exploration, but also collaborating, scholarly communication, disseminating, preserving, and so on. So a whole set of tools is needed for that, which the community has been constructing over the last 10 years. And I anticipate in another 10 years, we won't talk about eScience, because those tools which embody lots of computer science will just become the standard way of doing science. So eScience will become science. And so this is an interim phase, but I think that these paradigms are genuine, and that students who are doing data-intensive science need to know about a different set of skills. They need to know how to manage a petabyte. This is Jim's slide from Jim's talk. That was 2. He talked about fields like biology has computational biology, which is doing simulations of molecules and so on, but also bioinformatics, which is actually analyzing genomic data, for example. Similarly with chemistry, computational chemistry, chemoinformatics. And now you see many fields, like I'm going to a meeting next week in Australia on astroinformatics, for example. So there's new types of fields emerging because of this deluge of data which we need to get to information, to knowledge. And so this is Jim's slide, the generic problem. You have huge amounts of data. How do you classify it? What's a schema? For most people in science don't know what a schema is, how you organize it, may have to reorganize it, how do you share it, query, and so on. So these were different sets of skills that graduate students actually need to know to function as a data scientist. And these are part computer science, but Alex Saleh claims you need to generate not T-shaped people who know a depth in one area and only a little bit across other areas. You need, he says, pie-shaped people. So you need people to have a depth of knowledge of computer science, but you also need people who have a depth of knowledge of a particular domain. So this is what Jim was talking about in terms of his fourth paradigm. You see it in many places now. This is a professor at Santa Barbara, Jeff Dozier, who studies snow. It's interesting because of climate change that the snow line in the Cascades is going up 1 meter a year, and that means there'll be less water stored in the mountains for the summer, and there'll be more runoff in winter, so there'll be more floods, and there'll be less water in the summer, so it's really bad news. And this is actually how, in order to make conclusions, you have to combine data sets from all sorts of different areas and try and investigate and analyze it. So it's a very interesting article showing the need for actually combining data, using machine learning, using computer science tools to make serious predictions and estimations with errors of the future of, in this case, mountain hydrology. Hydrology is going, the water is going to be a major, major driver in the next 50 years. So, I mean, eScience was about the tools that you need to go and support this data life cycle, from acquisition, from collaboration, analysis, data mining, to publishing it, and finally to archiving some of it. That's the paper and the data. So Jim's vision was that what we should construct and what's the goal of all science, including computer science, is that you have some literature, and from the literature, which is all open access, so it's actually available in full text, and that's what the open access movement and the White House announcement that came in February requiring government federally funded research to make their papers available full text without a paywall after a certain period of embargo. So from the literature you can go to the data. So one of my goals is in Microsoft Research Cambridge, Georges Gontier solved the four-color theorem using theorem-proving tools, been solved by mathematicians before, and so with his proof, there's associated data. Similarly with science, with your paper, there's associated data. And what Jim wanted to do was to be able to go from the literature to the data, to add some data of your own, some analysis, you get new papers, new data, and you publish it and you get to the data. And his whole belief was that you could increase what he called the scientific information velocity. And having worked with many different communities of science over the years, it's quite clear there's a huge amount of inefficiencies in the way we do it. And talking to David Lipman, who is at the NCBI, the NIH, people who look after the National Library of Medicine, he does PubMed Central. I mean, the reproducibility of results in biology nowadays, life sciences, is really very scary. I mean, there was a study by Amgen, looked at 53 papers published in Science and Nature. They were only able to reproduce 7 of them. So a lot of things we need to do to make this efficient and more effective, to solve the problems of climate change, or at least understand the problems of climate change, and to solve problems of pandemics and diseases and things like that. So that's computer science, computational thinking applied to science. And I think there is a real role for computer scientists, at least teaching people their skills or actually working with scientists to go and try and solve some of their problems. And that's what Jim was doing. What's the future? Well, I'll just pick up 3 things which I think will be important: the cloud, machine learning, and conclude. So you must be aware that universities are building clouds. They're not the same as what Google and Microsoft and Amazon would call clouds, where they have hundreds of thousands of cores in huge data centers which are next to hydroelectric plants and, you know, very carefully cooled. But everybody's now using this cloud paradigm, and Microsoft, for example, has these data centers in the US linked by high performance, high bandwidth all over the world, and you get, when you store data in a data center, You get 3 copies here, but you also get 3 copies in another data center, so you have redundancy, and actually it's becoming a very useful model for industry, and many of the Fortune 500 companies are now using clouds routinely. In academia, it's been, much slower. Academics like to have their own cluster or their own supercomputer or whatever, and so I do believe it'll come. I've been slightly frustrated in that not many people run on Windows clusters. I'm well aware of that, coming from computer science department and physics. But actually, this year, Microsoft's cloud now supports Linux, Python, Java, usual sort of tools that you find in the computer science department and in science departments. So I now believe it's possible to do interesting stuff on infrastructure as a service on the Microsoft cloud. So we actually do have an initiative now, Azure for Research, and you can apply for a significant amount of time in Azure for free, and you can go and write a short proposal, a couple of pages or something like that, and it's analyzed every few months, and we try and make awards. So if you're interested, me or Harold can tell you more about that. And machine learning, which is the topic of this afternoon, is really important. I actually think parallelism in machine learning is even more important, but that's another issue. But so we all know computers are great for indexing the whole web. Microsoft, Google, and other people do it routinely. But what you need to do is computers to help us do things automatically. In PubMed, which is where the abstracts in the life sciences are put in the National Library of Medicine, there were 2 abstracts of papers deposited in PubMed every minute of the year. And there's no way you can keep up with that. So you need actually help to target, to alert you to interesting things, to make inferences. You may be looking for something, but the computer understands what you're looking for and can actually go and say, well, wouldn't you find this more interesting, and so on. So these are the sort of ideas and operations you need computers to help you do. And the combination of these things is extremely powerful. I was interested to find out that when you speak into Siri on your Apple or a Microsoft phone you speak in, what happens is that actually the processing can't be done on the phone, the machine learning to actually do the speech recognition. It goes up and is done in the cloud and comes back to you in less than a second. So it's remarkable that we can actually go and speak into a phone and you get the answer, but the computation, the heavy lifting, and machine learning has all been done up with deep neural nets, which is now what everybody's looking at, has been done in the cloud. So I think this is an example. This is just, a phone example, but you can imagine all sorts of different examples, both in science and in commerce and in everyday life, where you can use the power of the cloud to turn a small device without much processing power into something really powerful. So that is at least some of the topics for this afternoon. So to conclude then, what's the third age of computing? Well, there's a paper by Butler Lamson called What Computers Do: Model, Connect, and Engage. So what he says, every 30 years, there's a new wave of things that computers do. So he analyzes from 1950, 1980, what computers did was compute. They did simulations, like initially the ENIAC was used to simulate a model for a hydrogen bomb, for example, just to be concrete. You can read all about it in the book. And around 1980, we had the ARPANET, the internet, and in 1990 we had the web. So people were beginning to understand the power of computers. Now the computers have shrunk to mobile devices, handheld devices, and so on, for communication. So for the next 30 years, we've been exploring the use for computers with their power in connected devices. So that's what Butler calls the second age of computing. So simulation, communication. And what's happening now is that we're using computers in new ways. Artificial intelligence is one of them. Augmented human intelligence is another. Butler calls it embodiment. It's computers acting on your behalf, taking decisions that are useful to you, helping you find things you need. For example, you've all seen these ads on television for BMW and Mercedes, where the car brakes in an accident before you do. It actually acts on your behalf and does something useful. So computers then have begun to engage with the physical world in non-trivial ways. And there's huge ways of doing that. And that really is, I think, where we are now. That we have these sort of three ways. We spent 30 years learning different ways of computing in all the most generality, and then we connected them all, and we learned new ways of doing things in communicating, connected computers. And now we're actually putting intelligence in there in its weak AI sense, as opposed to strong AI, and is now giving computers new powers and systems which are going to be really exciting. And that's, I think, is the topic for this afternoon. And for me, it's really exciting, and understanding how you can get things which are simulating in more and more intelligence are clearly going to be really important. And so I leave you with this. My son did a PhD at Berkeley. He got infected in the Bay Area with startup fever, so he's gone back to London to do a startup. So at the age of 34, I'm still supporting him. I'm hoping one of these days he'll support me. You never know. So he has a thing which he calls Sketchinations. It covers all sorts of things. This is one he did about big data, machine learning, and the cloud gives informed, intelligent decisions. And that really is what industry want, what people want, informed, intelligent decisions. So I think this combination. If you want to find out more about these things, you can go to sketchinations.com. You can find out when you're doing exercise that the body uses, can absorb about a cup of water every 15 minutes. The rest is surplus, and all sorts of random facts. But this is one on machine learning. So I think this is the topic for this afternoon, and I think I've said enough. So thank you very much for listening.